We are Group 14 and today we'll be presenting a research paper titled Traffic Rule Violation Detection Using Machine Learning Techniques, published in the 6th International Conference on Communication and Electronic Systems, also known as ICCES, in 2021. So, this paper was written by P. Srinivas Reddy, T. Nishwa, R. Shivakiran Reddy, C. H. Shadwick, and K. Ritvik, all affiliated with the Department of Computer Science and Engineering at MLR, Institute of Technology, Hyderabad, India. Now, let's talk about why this research is important. So, urban areas have seen a massive increase in the number of vehicles, which leads to more traffic violations, especially signal violations, illegal turns, and red light jumping. Traditional traffic monitoring relies heavily on human observation, which is time consuming and error prone. This paper proposes an automated system using machine learning and computer vision to detect violations in real time through video analysis. The goal is to improve enforcement accuracy, reduce human workload, and make roads safer. The researchers have focused particularly on signal violations, and their system can detect when a vehicle crosses a red light, capture images of the violator, extract the vehicle's license plate number. Before jumping into the system, let's quickly look at the limitation of the current systems. Traffic police have limited visibility and reach. Manual photo capturing is slow and unreliable. Many violations go undetected due to human error. This is where deep learning based traffic monitoring comes in to automate and enhance the process. So, this is our methodology overview. So, key components are computer vision, which is used to detect vehicles and analyze video frames. Um, then deep learning, CNN plus RCNN, classify and extract features from vehicles. So next, GUI using T-Kinter, interface for police officers to monitor and respond. Software stack is TensorFlow, OpenCV, Python, and Tkinter.
Hi everyone, I am Sasna Manahara under registration number 4068. Now I will walk through the technical methodology of the proposed system. So, first module is image processing. The first step begins with raw video footage typically recorded from CCTV cameras at intersections. Each frame from this video is passed through a grayscale conversion to reduce the complexity of the image data, followed by a Gaussian blur, which helps smooth the image and reduce visual noise. This is step crucial because it is makes later object detection much more accurate. Next, system performs background subtraction. The technique compares the current frame to a reference frame in order to isolate moving objects. Basically, the vehicles on the road from the static background. Once we isolate moving objects, we apply binary thresholding. This filter out unnecessary pixels data, turning the frame into a clean black and white format. This simplifies the image further by highlighting only the relevant areas, typically the vehicle shapes. After that, we use dilation and contour detection. Dilation helps fill in gaps or small holes in the detected vehicle shapes, while contour detection traces the outline of those objects to refine their boundaries. The result is much cleaner and well-defined shape of each vehicle ready for analysis. Second module is object detection using RCNA. Once we have cleaned the image with clear vehicle shapes, the system uses a powerful deep learning approach known as RCNN or regional based convolution neural network. This process happens in three stages. First, the system selects region of interest. There are the parts of the image most likely to contain vehicles. Second, it extract features from these regions using convolution neural network, which helps identify complex patterns like edges, textures, and shapes that are unique to vehicles. Finally, each region is classified using SVM or support vector machine. This classifier determines whether the object in that region is a vehicle or not. What makes RCN especially effective is its ability to detect vehicles even when they are partially hidden or overlapping or moving quickly, situations that are mostly common in real world scenarios. Together, those two modules lay the foundation for detecting vehicles with high accuracy, and they set the stage for next phases, which involving identifying a specific type of violation and extracting the vehicle's license plate. Let's move to the next slide. So here, third module is vehicle classification. Once the system identifies the presence of the object, it uses neural network model to classify them into specific categories. The detected objects are classified into four types. Here, first two-wheelers such as motorcycles and scooters, then three-wheelers which are quite common in South Asian countries like Sri Lanka. Then the third one is four-wheelers, including cars, vans, and trucks. And finally, non-vehicle objects which could be pedestrians, street signs, or anything related to traffic violation detection. This classification is not just for organization, it's crucial because traffic rules vary often by depending on the vehicle type. For example, helmet rules apply only to two-wheelers, while seatbelts and lane disciplines are more relevant to cars and trucks. The fourth module is violation detection logic. After the classification, the system checks for any rule violation, specifically single violations in this case. Uh, it draws the virtual line in the road at intersections. If a vehicle crosses the line during the red traffic light, it marks as a violation. As soon as the violation is detected, the system crops the image, the offending vehicle from the video frame. The cropped image becomes focus for the next step, identifying the vehicle. The entire process is remarkably fast. The average runtime is just 6.55 seconds, making it efficient enough for real-time deployment in urban traffic environments. The last one is license plate recognition. Once we have cropped the image of the violating vehicle, it goes through a license plate recognition process. This involves OCR pipeline or optical character recognitions. Before reading the text, the system uses OpenCV to enhance the image quality, adjust contrast, and then sharp the visual features from the number plate. Once the image is optimized, OCR tool applied to extract the actual license plate number. This allows authorities to directly identify the vehicle and its owner, enabling quick and accurate enforcement actions. So, to summarize, the system not only detect violation, it also identify who committed it with high efficiency and reliability. Let let's now move to the final part of our presentation. Then where we discuss the conclusion, further improvements, and the real world impact of the system. Thank you.
Then let's see about the system architecture and workflow for detecting traffic rule violations based on image processing. This process begins with CCTV footage being fed to the system. Then they use CNN to identify moving objects in the frames. Then in the next step, it is determining if an object is a vehicle. If so, moving vehicles are detected using a region-based convolution neural network. Next, images are classified using support vector machine. Then the system checks for any violation rule using the predefined rules by the system. Upon detection, appropriate actions are taken against the violation. License numbers are extracted for identification, and the interface allows for either manual or automated reporting. The entire detection process runs with impressive runtime efficiency, completing in approximately 6.55 seconds per incident. This workflow showcases the power of integrated image processing technologies in real-time traffic rule violation detection. When we talk about the architecture of the convolution neural network, as depicted in the table, we can see that the model is designed for image classification. Starting with an input size of 224 by 224 by 3, which is representing a color image with 3 channels. Normally, it is an RGB image. The network employs a series of convolution layers, both standard and depth-wise, with stride 1 or 2 to adjust the spatial dimensions. The filter shapes are varying from 3 by 3 by 332 to 3 by 3 by 1024, increasing the depth to capture complex features. Depth-wise convolution optimize the computation, while average pooling reduces spatial dimensions to 7 by 7 by 1024. This process creates a fully connected layer and a softmax classifier, outputting probabilities for 1000 classes. This design showcases the power of CNN in visual recognition tasks, which used in moving object identification in here.
The system was successfully tested on real CCTV footage and detect traffic signal violations automatically. When the system processes input video from a traffic camera, it first reprocesses the frames and draws predefined lines to define the stop line. Whenever a vehicle processes this line during a red signal, the system captures a photograph. It then crops the image to focus on the vehicle, removing unnecessary parts. Using an RCNN, the system analyzes the cropped image to confirm the violation and can also extract the vehicle's number plate for identification. This approach ensures accurate automated detection of signal violations and provides clear evidence for enforcement. To conclude, this research presents a working prototype that uses computer vision and machine learning to detect signal violations automatically. It has the potential to reduce the workload of traffic policy, improve safety, and enforce traffic rules more effectively. In the future, the authors plan to expand the system to detect helmet violation, illegal parking, wrong-way driving, and even include a penalty point system that keeps track of repeated violations based on the number plate recognitions. They also mention using faster computers or GPUs to further reduce the processing time and applying advanced techniques like OCR for better number plate detections. Overall, the system represents a major step forward in using AI to improve road safety and traffic law enforcement. This is all about our research paper discussion. Thank you.